Alright, so 7.3 is a 10 to the 5th gigabecquerel source emitting 1 MeV photon per transformation is uniformly distributed on the surface of a hypothetical sphere of 2 meters in diameter, entirely within a water medium. At the center of the sphere, find all these things. So we have a surface of a sphere. I don't know how to draw spheres, but let's go with that. We're looking for stuff inside the middle here. There is a 2 meter diameter, which means that R is 1 meter. And the source is distributed across this sphere. So it's a 10 to the 5 gigabecquerel source emitting 1 photon per transformation. So 1 gigabecquerel, 10 to the 9 becquerel, and there's 1 photon per transformation. You get 10 to the 14 photons per second, and they're 1 MeV. And it's uniformly distributed across this sphere. So, and this is all water inside here. So we want to find the flux and then a bunch of different kermas and different types of doses. So since we're looking for what the values are here in the center. So since every single point on the surface of the sphere is exactly 1 meter away from the center, we can simplify this and just say it is some point with a source 1 meter away with the exact same value. Does that make sense why we can do that?
Because it's equal distance.
Yeah, everything's equal distance. So we want to find the uncollided flux. So this is pretty simple. We're just going to have our source strength over geometric attenuation, 4 pi r squared, e to the minus mu r. So B is 10 to the 14. This is per second, 4 pi, 100 centimeters. We always use centimeters for everything, so squared times e to the minus, and mu for water from should-be-till is 0.07066, and 100 centimeters. So we get that the flux is, the uncollided flux is 6.8 times 10 to the 5 per centimeter squared per second. Any questions on that? Yeah.
Yeah. How we imagine that the whole number of photons concentrated in one point while it's distributed through the whole surface?
Because every point on this surface
You can
is
just do
exactly
the
1
integral.
meter. Every single point on this surface is actually 1 meter away.
Uh-huh.
So if we wanted to say that this was an area source, this is the source of the shell. It's over 4 pi r squared is the area of that sphere,
Okay,
right?
okay.
So if we wanted to find out the per area source of this, it's going to be 10 to the 14 divided by 4 divided by pi divided by 100 squared, or yeah, 100 squared. So it's going to be 7.96 times 10 to the 8 photons per second. So this would be our area source strength. So if we wanted to say across the whole thing, so let's say we have
I have to make the integration.
You wouldn't have, you could integrate. You could integrate through. But if let's say so you have an area source, so that source is it's going to be the source strength per area times the area that it's across. So times 4 pi r squared, and then divided by your geometric attenuation times either negative UR. So if you plug in S over A was just 10 to the 14 over 4 pi r squared. It's 10 to 14 over 4 pi r squared times 4 pi r squared over 4 pi r squared times e to the negative mu t, or mu r. And so you end up with the exact same thing. And you'd end up with the exact same thing if you said it was, if you did over 4 pi d omega, if you did, it'd be the same thing if you did it over the whole sphere. That makes sense? Okay. So next, we want to find the Kerman water. Is that what that says?
Yeah.
So to find the Kerman water uncollided is just going to be the response of H2O times the flux. Pretty straightforward. From shield detail, you get R is equal to, is that 0.4984 times 10 negative 9 centigrade centimeter squared. So you get that K of H2O uncollided 3.4 times 10 negative 6 gray per second. It's pretty straightforward. That to find the Kerma rate, these are rates. To find the Kerma rate in water, it's exactly the same thing. The response in the water in the air, which is the next one. Sorry, response in the air is 0.4481 times 10 to the negative 9 centigrade centimeter squared. And I converted that to centigrade in order to give the answer. That's 3.044 times 10 to the negative 6 grade per second. Large dose. Never mind, it's not too big. Same thing for the exposure rate. Exposure rate times R, rate exposure times flux. R is just 0.5. 118 times 10 negative 9 R centimeters squared. 0.5, yeah. That's how shield utility.
Right. For the Kerma rate at air, we're gonna use the phi node that we got before.
Use the what?
The phi node.
Yeah, always use this phi. Use it for everything.
Okay, but here in the phi node, we use the attenuation by water. We use the mu of water.
Yep.
So how are we gonna use it with the?
So, okay.
Did you get what I mean?
Yeah. Okay. So this was something that we always have trouble being okay with whenever we're doing these dosimetric quantities. This is what physically is happening, and this is what physically is happening here. All of these are hypothetical. All of these are saying if we take a Kerma detector or a Kerma meter, I don't know how they actually measure it, but if we want to know the dose in water, we would take a little small piece of water and measure the Kerma in here. If we wanted to know what it was for air, this little detector would be an air detector in here, right in the very center. So it's kind of weird thinking about this for air and water, but let's say if our medium is air, and we calculate the flux, and you know what's the dose a person's going to get out there. Well, Kerma of water is going to be a better representation than Kerma air because we have a bunch of water in us. So we're going to be more represented by this. So we can find the Kerma in water inside the air medium using the flux that we got from the air medium, but we're not interested in the air Kerma. We're interested in the water Kerma. So we just multiplied this flux by the response function. The response function just tells you how much dose you're going to get per flux, basically. So dose per flux. So for water, you're going to get a certain amount of dose per flux for 1 MeV photons. Same with air, you're just going to get a different value. But the flux is actually what's going on in the actual system, in the actual problem, not necessarily the dosimetric quantities. Does that make sense?
Can I try?
Yeah.
Okay, so so like his person example, you want the Kerma at the center. So like if a person was in there.
Yeah.
So you need to find it with the R values for that. But the entire medium isn't made of person. So like you have the person in the middle with water around them. So the flux through the water is the same, but the Kerma you're looking for in the very center. So that's why we're able to use the different medium at the center, with the flux still going through the water.
So he's talking about the situation at the center, what's going on at the center?
And that's where the Kerma, but the flux getting to the center
I know.
is still through the water.
But he just said in water and in air, he didn't specify this in the board. It's okay, I understood what you
Okay.
There's not a problem with the medium is?
It does
Okay, so,
That,
okay.
yeah, that's part of the definition of Kerma, like you have to say the air Kerma or the water Kerma. Maybe I'm not.
Yeah, it's, okay. The last one is the total response, or the total exposure. For example, exposure is always measured in air. Exposure is always air. So it's okay to do it for that for other materials. So because this distance between the source and the center point is always the same, you can use one buildup factor for that. You don't have to integrate the buildup factor. So exposure is going to equal the flux times the buildup factor times the response, which this is just equal to, it's just going to be this value times V. The uncollided, this value is going to be this value. So here's a time where you can use the buildup factor from shield utility. So the Berger approximation for buildup factor at 1 meter, 1 MeV water, and I think you have to put all of these in here, is 14.67.
Close. Pretty close. 15, you want me to break it?
Yeah.